This is the second of 3 videos about Galois theory. If you haven't seen the first video and haven't taken a course in Galois theory, go ahead and watch that one first. There's not much that you need to know from that video besides what a Galois group is, so if you know that, then let's continue to the second half of the series. So this is how a typical Galois theory course goes. You learn a lot of stuff and you prove a lot of stuff and you end the course and you're happy, even though you have no idea how to apply it in any sort of practicality, and there's so many questions left unanswered, like, how do I find the Galois group? How do I prove it's the Galois group? How do I find these redundancies? How do I know whether or not the roots of unity I need are actually in the splitting field? How do I find them within the splitting field? We're going to answer all these questions in the next 2 sections with a couple of examples. The first example we'll start with is to solve this degree 5 equation here. X to the 5th plus 10x cubed plus 20x minus 4 equals 0. You give this problem to a lazy mathematician who thinks he's better than you. He'll wave his hand at you and say, it's degree 5, it doesn't have any solutions you can write down. But if you give it to an overachieving Olympiad student who thinks she knows better than you, she'll say, plug in x equals t minus 2 over t. Doing that gives this, expand it out, and combine terms, and cancel down to this equation here. We can factor this into t to the 5th minus 8 times t to the 5th plus 4 over t to the 5th. So t is either the 5th root of 8 or the 5th root of negative 4, and in either case, x gives 5th root of 8 minus 5th root of 4. So the mathematician is right in that quintics generally aren't solvable, and the Olympiad student is right in that this one is, with the solution she gave us. But neither answer is really satisfying. How do we solve this using Galois theory? No tricks that aren't applicable to just this one problem. This is what we'll be doing in this section. Be warned though, there will be some heavy algebra manipulation, because for cleverness we substitute brute force. Therefore, any calculations we do in this chapter will be done with a Python program I was able to write myself, not using Mathematica or Maple or Sage or any other computer algebra system, just to show that lowly humans can do Galois theory with just their wits and Python. To do so, we'll set out a 5-step program. The first step is to compute the Galois group of the splitting field L. Once we have that, we will discover that zeta 5 is already in the splitting field, so we won't need to adjoin it. Step 3 is to prove that we have the right Galois group. Notice that we didn't do that in step 1. This will be explained later, but we'll get a probable answer for the Galois group in an easy way, and then prove that it's the Galois group in a much more tedious way. In a similar way, step 4 is to find zeta 5 in the splitting field. Again, we'll have a very good heuristical argument that says that zeta 5 is in the splitting field, but then step 4 is to actually write it down in terms of the 5 roots. And finally, step 5 is to use the Kummer theory trick to actually generate the solutions. The Kummer theory trick was explained in the last video, but this video will be self-contained in that regard so you can follow along without having seen it. So let's start with step 1, to discover the Galois group. One thing we know we can do is factor the polynomial mod large primes. This can be done with the Cantor-Zassenhaus algorithm. For any specific prime p, if we look at the ring of polynomials mod p of x and take this ring mod p, this will split into factors based on the factorization of p of x mod p by the Chinese remainder theorem for co-maximal ideals. And then each of these factors are finite fields, and the Galois group of a finite field is cyclic generated by the Frobenius endomorphism, or raising everything to the pth power. The order of this on any finite field is equal to its dimension over z mod pz, so the Frobenius endomorphism acts as cycles equal to those dimensions. That was a lot of words that were at a very high level, so the conclusion is that for every prime p, there is a special element of the Galois group of p of x called the Frobenius element, so that the size of the root permutation cycles of this Frobenius element are exactly the degrees of factoring p of x mod p. And we care about that because the Chebotarev density theorem says that the Frobenius element is uniformly distributed among all Galois elements as the prime goes to infinity. So what we'll do is factor p of x mod a lot of primes, and use the relative densities of the factor degrees to tell us what the Galois group has to be. We'll do a few examples, starting with 7. P of x factors as this mod 7, and both factors are irreducible. so the Frobenius element for 7 cycles 4 of the 5 roots. As another example, try mod 11. In fact, p of x is irreducible mod 11, so the Frobenius element here is actually a single 5 cycle. Then looking mod 19, we get a linear factor and 2 quadratics, so the Frobenius element for 19 consists of a pair of 2 cycles and a fixed element. And then finally, we get our last cycle type with 151, where the polynomial factors completely, and hence the Frobenius is the identity, where every element is in its own 1 cycle. So then, as mentioned earlier, we can factor this polynomial mod a large number of primes with the Cantor-Zassenhaus algorithm. Here, I give statistics for the first 2,000. For technical reasons, we exclude 2, 3, and 5, because they give repeated roots and their composite quotients aren't all fields. Anyway, among the first 2,000 primes, we see that the 1, 1, 1, 1, 1 cycle type is attached to 96 primes, a proportion of approximately 1 over 20. So that sort of implies that the Galois group has order 20. And we can glean that about half of the primes have a 4, 1 cycle type, so 10 of the 20 elements in the Galois group permute 4 elements in a cycle, and 5 form pairs of 2 cycles, and 4 are 5 cycles. As an aside, the speed at which the error of these counts off from their required values tends to 0 is directly related to the generalized Riemann hypothesis, where instead of the zeta function with all 1s in the numerators, we use other numbers and still look for zeros along the critical line. Anyway, let's figure out what the Galois group is. Start by labeling the roots so that the 5 cycles permute R1, R2, R3, R4, and R5 in a cycle, and its powers. When you conjugate by any other group element, applying it, then the 5 cycle, then its inverse, all that does is relabel the 5 cycles roots via the other group element, so what remains is still a 5 cycle and is still in the subgroup. The point is that among all permutations of the 5 roots, the only ones that conjugate this 5 cycle to one of its powers is 20 of them, which must be the 20 elements of the group. Why 20? Because, as we just said, conjugation acts by relabeling. So we can choose where R1 goes, and then where R2 goes, and then we've determined the 5 cycle already, so there's no other choice involved. 5 choices for where R1 goes, and 4 where R2 goes, gives 20. And hence the Galois group is composed of exactly these elements, and digging into the details, we determine that the elements act via linear transformations on the indices. By the way, this is called the Frobenius group of order 20, same guy, but unrelated to the Frobenius group elements. The next step of our agenda is to prove that zeta 5 is already in the splitting field. To do this, we return to the chart of cycle types. If you studied it before, you maybe noticed that the primes in the top row all end in 1, the second row ends in 9, the third row ends in 3 and 7, the fourth row ends in 1. That is, the primes appear to factor based on what they are mod 10, or mod 5 since all primes are odd other than 2. To use this, we use 2 facts about the set of split primes. The split primes are the primes that the polynomial factors completely, the ones of the 1-1-1 factorization type. It turns out that except for the primes we exclude at the beginning, here those being 2, 3, and 5, the primes for any polynomial that generates the same Galois extension are all the same, so the split primes depend only on the field itself, not the specific polynomial. The important fact is that if one splitting field K is contained in another L, then the primes that split in L also split in K. That is, going from fields to split primes is an order reversing map. This should make sense if we think about the roots of the polynomial mod p as sort of avatars for the actual roots. For some generator polynomial for L, we have avatars mod p for all the roots, and so for any element of K, we can compute it in terms of the roots of L, and hence we can get avatars for the roots of K by using the avatars for the roots of L in the same expressions. So if a prime p has all roots for L, it should have all roots for K also. And the second fact is that the split primes for this specific field Q adjoins zeta n are exactly the primes that are 1 mod n. This should also make sense with the avatar interpretation, because if the polynomial for zeta n splits mod p, z mod p has an avatar for zeta n, which is an element whose nth power is 1, and for whom no lower power is 1, Say the avatar is a, then a to the n is equal to 1, but also a to the p minus 1 is equal to 1 by Fermat's little theorem, so p minus 1 must be a multiple of n, which is exactly the condition that p is 1 mod n. So combining these, we know that L contains the fifth roots of unity because the split primes of L are also split for the fifth roots of unity. If you're eagle-eyed, you notice that we only provided an argument for the exact wrong direction for each of these facts, but the converse of each of them is also true, so our conclusion does work. Before we move on, let's standardize some long overdue notation. If we have a cycle, say this one here, instead of writing this every time, we collapse it into this much more compact form so that we can write it down easier. And since permutations are really functions that take one root to the next, we apply them right to left because right to left is the same as inside to out. So this product is more compactly written as 1, 2, then 1, 2, 3. So let us return to our polynomial and consider step 3 of our plan. We know what we think the Galois group is. Now let's prove it by bashing out redundancies beyond what Vieta tells us. Let's take this proposition. It says that if a given root permutation is a Galois element, then if we're given anything in K, the root permutation fixes it. We replace the implication with a not or, swap the or operands, re-replace the implication, and replace the inner implication with an and, we get an equivalent statement. It says that if we can find some element of L that is still in K but isn't fixed under phi, then phi can't possibly be a Galois element. This is somewhat obvious, but it will help us reduce the possible Galois elements. In particular, we'll find a polynomial in the 5 roots, R1 to R5, that is fixed under all of F20, but not under anything else. If that element is rational, but under no other permutation of the roots is it the same number, then we've culled the possible set of permutations in the Galois group to F20. The next obvious question is, how do we construct such a polynomial of the roots? The idea we'll use repeatedly is that of projecting, or averaging. We take some random polynomial, usually a single monomial, and apply the whole group to it. That gives us 20 monomials. If we add them, then applying anything from the group just permutes the terms of the sum. We'll pull up the polynomials we have values for, because of Vieta, for reference, and test the idea on this monomial. Here's the 20 Galois elements, and we apply them all to get this. This polynomial is fixed under everything in F20, and nothing else. So this should be a rational number. We can't learn its value from the Vieta formulas, but we'll go into how to compute that later on. In any case, this is too complicated for us. We'll turn the above operation into a general procedure with a name, taking the sum of the Galois elements and calling it the projection operator proj. Applying it to some small monomials, we get proj of R1 is this, which we already know is 4a. If we try proj of R1 squared, we get this, which again, we already know is 4a squared minus 8b. Maybe mixing some terms will be better? Proj of R1 R2 is this, but no, we know that equals 2b. So what does work? It turns out that the first monomial that gives us something we can use is proj of R1 squared R2 R5. Writing down what proj is, distributing the monomial, and acting, we get this sum here. Of course, each term is counted twice, so we'll actually work with the projection divided by 2, this sum here. We have values for a through e, the Vieta symmetric sums, so we'll call this symmetric sum f. We should believe that f is rational because it's fixed under the whole Galois group, but how do we determine its actual value? Let's consider the situation we're in right now, because it will reoccur 2 other times. We have a large group G and a smaller group H. What do we know about them? We know a lot about the polynomials fixed under G, the fully symmetric polynomials, but we want to know about the polynomials fixed under H. If we had one, we'd like some way to find its value. The solution every time we hit upon this problem will be the same. Take the element you have and apply every element of G to it, and look at the polynomial with all those as roots. I'm sort of fudging here because tau should actually iterate over the left cosets of H, but this is good enough for this explanation. We won't always get Z back, since Z is only fixed by H, But if we expand out the polynomial, the coefficients should actually be fixed under all of g, since they're symmetric sums of all the g applications of z. So applying anything of g to any of them just permutes the summands and changes nothing. But we said we had perfect knowledge of everything fixed under g, so we can write down the coefficients to our heart's content and get a polynomial for which z is a root. In our case, g is the full symmetric group and h is f20. We'll prove a lemma to help us determine when g elements actually give us different permutations of z. Every permutation can be written as the product of something that only affects 3, 4, and 5 with something of f20. Here's a proof. Essentially, we choose sigma so that sigma inverse mimics where tau inverse sends 1 and 2, and that's good enough. Let's do an example instead. Say tau equals 142 times 3, 5. So then tau inverse is just tau, but the number's reversed. So it's 241 times 5, 3, or 124 times 3, 5. So since tau inverse sends 1 to 2 and 2 to 4, so should sigma inverse. Then since f20 acts by linear functions on indices, this linear function should be multiplication by 2. As cycles, that's 1, 2, 4, 3. Then tau times sigma inverse is this product, and working it out from inside out, 1 goes to 2 goes to 1, etc. The product actually is 3, 4, 5. We move sigma to the other side, replace it with 1, 2, 4, 3 inverse, and determine what that is, and we've written tau as the product of a permutation of 3, 4, and 5 with a permutation in f20 as we wanted. You can check it yourself that this product does equal 142 times 3, 5. The reason we care about this lemma is because if we apply any one of these to f, the sigma hits it first and does nothing, since sigma is an f20, which f is fixed by. So all the different elements are given through only permutations of R3 through R5. So then actually applying these 6 permutations to f, we get these 6 polynomials. Remember, the point was to look at the polynomial with these as its roots and expand it out. This should be doable because the coefficients are fully symmetric in R1 through R5, and we have the fundamental theorem of symmetric polynomials. It says that any polynomial that is fully symmetric in all the roots is actually a polynomial in the coefficients a through e. If you've never seen this before, a quick proof: we look at the monomial with the largest exponent of R1, then tie-break with the largest exponent of R2, etc. This gives an ordering of monomials in the polynomial. Then if the exponents of a given monomial are u1 through u5, we consider the expansion of this here. A to the u1 minus u2 times b to the u2 minus u3, etc. The claim is that this expansion contains a term of type x, and that's the largest monomial inside this expansion. So we can subtract off the correct multiple from the symmetric polynomial we're looking at. It kills off one monomial and doesn't introduce any larger ones. So we keep doing that until we reach 0, and then we're done. We'll show a 3-variable example, r1 cubed plus r2 cubed plus r3 cubed. The leading monomial is r1 cubed, which corresponds to a cubed. So we add and subtract a cubed and expand to get this. Here the leading term is the minus 3 r1 squared r2, corresponding to ab. Then we subtract and add 3ab, expand, and all that's left is 3 r1 r2 r3, which is clearly 3c. Thus we've written this sum of cubes in terms of the symmetric polynomials. We can do the same thing for the polynomial we wrote down earlier. It's a much larger polynomial because the degrees of each term is higher, but I was able to write a Python program to handle it without issues. To see it written out, here it is. But we know each of these variables' values by Vieta, so we plug them in and get this polynomial here. It turns out that 40 is a root of this, and is not a root again if you divide by x minus 40, so it's a simple root. It turns out that the rest is irreducible, but we don't need to know that, only that 40 is a simple root. What we actually learned from this exploration is that only one of the 6 polynomial permutations is actually equal to 40. We've sort of been loose about our choice of root ordering, so let us fix an ordering of the roots so that it is this polynomial permutation that equals 40. But we also conclude that the Galois group can't have anything more than f20 in it, or else the other elements would have also sent 40 to 40, and none of them did. We can also prove the Galois group can't be smaller than F20 by looking at every maximal subgroup of F20 and finding expressions symmetric under those, but not the full F20, doing the same root computation, and learning that that polynomial has no rational roots. I won't do that here, and you'll just have to take my word for it, that the Galois group actually is F20. And now we begin the most tedious part of our journey, step 4. Find zeta 5 within the splitting field. We'll deploy a 3-part strategy. First, we learn everything there is to know about polynomials fixed by F20. We know f, so that's a start, but we'll need a full library of functions to do further calculations. Next, build an element in the same way as we just did that's fixed only under the Galois group that fixes zeta 5, and thereby find something in Q adjoin zeta 5. Finally, we use that element to somehow backwards engineer what zeta 5 truly is. So we begin with the first step. We need to know everything about everything fixed by F20. The fortunate thing for us is that the projection operator is idempotent after dividing by 20. That means that if we apply it and divide by 20 to anything already fixed by F20, we get the same thing out, because applying it just creates 20 of the same summands again. So to find everything fixed by F20, we can just look at the output of the projection map. And it's even good enough to look at the projection of monomial terms, so that's what we'll do. So first, we reestablish what we know from Vieta in this exploration. We'll set it aside for now, and ponder the question of what we actually know about the full ring of invariant polynomials. We know that A through E are basically independent from each other, and F satisfies a degree 6 equation, the one we used to construct it in the first place. And actually, by the fundamental theorem of Galois theory, knowing F is enough. F is fixed by F20 and nothing else, so the field it generates inside Q of R1 up to R5, along with A through E, must be the fixed field of F20, and hence everything in the field fixed by F20 is a rational function in A through F. Thus, we've shown everything we want is actually at most a degree 5 polynomial in F, with rational coefficients in A through E. We can't actually force P0 through P5 to be polynomials because the degrees of F grow too quickly and we miss a lot of stuff. We'll see that later. But rational functions are icky. Is there an actual basis, not just powers of F, so that we actually do get true blue polynomials in A through E? We care about this because they're easier to enumerate. We can iterate through all products of positive powers of A through E very nicely, whereas the denominator of a rational function might be anything. And the answer to our question is, yes, there is a better set of functions, F through J, that give us everything. For those who know what this means, the polynomials fixed under F20 are a free module of rank 6 over the S5 invariant polynomials, with generators 1, F, G, H, I, and J. And let me make a point here. We're never multiplying F with G or any of these generators with any other. It's nice that it turned out that way, but it'll be useful later because polynomials will be only linear in each of these F through J, and we'll need some linear algebra. I'm just going to flash this up here. We can do some pre-work and figure out the degrees of the polynomials will be 4, 5, 6, 7, and 8, using what's called Molien's formula, but I won't go deeper into it than that, and we'll learn this through trial and error anyway. So we have our goal, write everything in terms of F through J. In particular, we want to compute the powers of F in terms of F through J, because we have values for the powers of F, and we can invert that knowledge to give the values of F through J. So what we'll do is going to be a 4-step process. First, for every degree from 0 to 20, because f to the 5th is homogeneous of degree 20, we'll just create a list of the terms we're allowed to use up to that point, in terms of A through J. For each of those monomials, we expand it out in terms of R1 through R5 and keep track of the highest monomial term it has. In essence, we're creating a lookup table from monomials in R1 through R5 back to monomials in A through J. We did the same thing with the fundamental theorem of symmetric polynomials, except the dictionary was trivial to build because we had an algorithm for it. So we build this dictionary whose keys are monomials in R1 through R5. But inevitably, there will be some overlap, so if two expansions of a through j polynomials have the same top monomial, we just subtract one from the other, and repeatedly do so until it's unique again. We'll see how this works in practice a bit later. Then, once we've constructed the whole dictionary, if there's a leading monomial that isn't hit by anything, that's how we'll build up the polynomials that become f through j. So there will be one leftover monomial in degree 4, whose projection will become f, and one leftover of degree 5, whose projection will become g. The fact that we only need 5 extra terms to go off to infinity is kind of bonkers if you think about how haphazard this process is, but that's math for you. Anyway, going up to degree 20 with our lookup table, we'll be able to decompose the powers of f into polynomials in a through e times f through j, which we'll write in this matrix form. And then we're solving mx equals b, where we know m and b, so we just invert the matrix to get f through j. And then with this huge dictionary, we'll know everything about every f20 invariant polynomial we would ever ask. So let's begin the process to show how it works. We'll go up to degree 8. Obviously, there's only one term of degree 0, so we've locked that down. Then the term with r1 as the leading monomial is a, and there's no others of degree 1, so we're done there. For degree 2, there are two monomial types, r1 squared and r1r2, and they are a squared and b. For degree 3, we're still learning nothing new, 3 monomial types. Then for degree 4, we finally get a bit off the beaten road. We get 5 normal monomials, but projecting r1 squared, r2, r5 doesn't include any of those, so it gets its own variable f. And that is why we chose this particular monomial originally. It was literally the first one that projected to something not determined by a through e already. Then for degree 5, we continue, except notice we include a times f as one of the monomials. If we look over all the possible monomials, we again notice that r1 squared, r2 squared, r4 doesn't average out to include any previous monomial, so its projection becomes g. And degree 6 doesn't give us anything exciting except for avoiding this monomial, whose projection becomes h. And then we run through the monomials for degree 7, same as before, except wait! We've seen this last monomial before. The monomials for cf and ah are the same. So we take the difference, and the leading monomial of this difference includes r4, r5 instead of r3, r5, so it is again unique. And that's all the monomials in degree 7, except r1 cubed, r2 squared, r5 squared, which hence becomes the variable I. And we begin our excursion in degree 8, and oh my! We've seen this monomial before too. Cg and b squared d have the same top term, so we take the difference, but yikes! We've seen the leading monomial of this difference before too. So we subtract bh, get uniqueness, and keep going. But we're caught again! df and abe have the same leading term, so we subtract for the last time and get our final missing monomial, whose projection we call j. And now you can take my word for it that doing the same process up to degree 20 will never fail, and we'll never come across another missing monomial, but animating it is boring, and there's a ton of monomials after this point, and it's not worth showing. But now we can consider the expansion of f squared. Our strategy was to repeatedly match the leading term with something in our dictionary and subtract, so I'll stop yapping and let it play through. And we're done. We wrote f squared as a sum of things in terms of a through j, and we can plug in f equals 40 on the left side and the zeta values for a through e on the right to get this. If we do the same for the powers of f from 0 to 5, we can put them together into this matrix equation like this. Notice the first row is 1 equals 1, and the second is f equals 40, so we're not being dumb and losing anything. But we can solve this by row reduction or matrix inversion, and we end with f being 40 like we knew, g being 40, h being 200, I being negative 160, and j being negative 800. And remember, we wrote everything of degree up to 20 in terms of a through j, so we, at least in the abstract, know the values of every f20 invariant polynomial we could ask for. Just for reference, we'll collect the full list of single variable monomials we know into a list. Now that we're finished with that, we can move on to the second step in our three-part strategy. Use this knowledge to find an element inside the zeta 5 field. To get our bearings, let's fill out the subgroup lattice for F20. Again, this is an abstract question we can do without reference to any field theory, or we could look it up, because all we're doing is talking about groups. On top, you have the full F20, remember, given by linear transformations of the root indexes mod 5. Below it, you have 5 sets of transformations, those that fix one of the roots R1 through R5. And then, also to the right, you have the linear transformations that instead of any leading coefficient, you only use plus or minus 1. That intersects with the other 5 to give 2 transformations with each leading coefficient plus or minus 1 that fix each root. And off to the right side again, we have the linear transformations where each root index just increments by a fixed number. These are the 5 cycles we originally constructed F20 around. Then all that's left is the single identity. Now how do these translate into fields? The top is obvious. The field fixed by every Galois transformation has to be the rationals. The weird one below it to the right ends up being q adjoins square root of 5. We aren't surprised by this because quadratic reciprocity says that the split primes for q adjoins square root of 5 are those that are 1 or 4 mod 5. So q adjoins square root of 5 must lie between q and q adjoins zeta 5. Remember whose split primes are the 1 mod 5 primes. We don't really need to know what this field is for this analysis, but it's nice to have. And then the one below it has to be q adjoins zeta 5 if we're correct. And then the 5 below q certainly have to be q adjoin each of the roots. And notice that these are all separate fields because as complex numbers, there's no reason that any of these should be the same. In fact, one of the roots is real, so the others that are complex certainly can't generate the same field. Anyway, then the 5 fields below are just the composite of each root field with square root of 5. And again, we don't really care about those fields. And the field on the very bottom is the splitting field q adjoins zeta 5 and R1. Again, assuming we're right about zeta 5 actually being in the splitting field, this is what the field tree fills out as. And now notice we're in the same position as before. We have a large group F20 and a small group of the 5 cycles, and we want to know something about the polynomials fixed by the smaller group. Remembering our solution from last time, we construct the projector by adding the elements of the smaller group, and applying it gives elements fixed by that subgroup. In this case being gal of q adjoins zeta 5 and R1 over q adjoins zeta 5, meaning elements of q adjoins zeta 5. We'll apply it to R1 squared R2 to get this. Then we again apply the whole of F20 to this and get 4 different values, these here. We then take the polynomial with these as its roots, whose coefficients are fixed under F20. Using our library, we get this degree 4 polynomial, and plugging in our values for a through j, we get this. Wait, what? The polynomial is x to the 4th equals 0? What does that mean? It means that all 4 of our roots we constructed are 0. Is that okay? We were expecting an irreducible polynomial, and we got this very reducible polynomial. But it turns out that there is no problem, because while the roots are all 0, that just means that 0 is fixed by all of F20. If it had had other roots besides 0, that would be a problem, because then there would be a supposed Galois element that doesn't fix a rational number. But we just hit a weird edge case where there's not actually a math contradiction, but it's not what we wanted. So let's move on and choose another monomial to project. The monomial we choose that ends up working is R1 squared, R2 squared, R3. And then we divide by 20 because it'll end up making the end polynomial come out nicer, but we gotta remember that that's what we're doing. We can go through the whole kit and caboodle again, but we understand the idea, and we find the polynomial to be x to the 4th plus x cubed plus 11x squared plus 11x plus 31. We'll let the roots of this be b1 through b4, again allowing ourselves a bit of ambiguity to be determined later. We'll let b1 be the projection we wrote down, though, leaving the others unchosen. Remember, the point of this was that we believed that zeta 5 would end up being in this field, and now our next goal is to show that. Just for reference, we write down the polynomial that zeta 5 satisfies, along with its square, cube, and fourth power. If you've never seen this before, it's just the polynomial you get when dividing x to the fifth by x minus 1. Well, that's not helpful. What'll we do? Here's where we are. Our usual strategy is to write down a polynomial in B1 through B4, apply the whole current Galois group, and figure out, no, I'm tired of doing that. We don't give a flying fladoodle about the BI. They're just a vehicle to getting to the zeta. So let's make the assumption that we're right and say B1 equals C1 zeta plus C2 zeta squared plus C3 zeta cubed plus C4 zeta to the fourth. You might be confused why we're using that form instead of 1 zeta, zeta squared, and zeta cubed. It's more symmetric this way, and it doesn't make a difference. And then we know the Galois group of Q adjoin zeta is cyclic of order 4, where the generator sends zeta to zeta squared. Call that generator rho. And applying it twice takes zeta to the fourth, 3 times takes it to zeta cubed, and 4 times takes it back to zeta. So then we let B2, B3, and B4 be the roots we get when applying rho to B1. And now we're a bit stuck. What do we do? Well, here's where we pull out the only small idea that isn't generally repeatable. Let's look at zeta times B1. Applying rho, splitting the product, and applying rho, we get zeta squared times B2. Applying it again, we get zeta to the fourth times B3, and one more time gives zeta cubed times B4. So these 4 are conjugates. And similarly, these 4 quadruples are all conjugates. So what? Here's where the idea comes in. We add them. They should all be rational numbers, and each sum equality should give us an equation in the C coefficients. Our old idea comes in again. We compute this product of x minus each of the sums. But this doesn't end up working, and here's why. We know that the BI should have some sort of redundancies that show us that their Galois group is cyclic, but we don't know what those are right now. We literally know nothing about the BI right now, so there are actually 24 conjugates we'd have to use. Instead, let's look at this product. This is better. The conjugates of zeta B1 are exactly these 16, even without any knowledge of any BI. And expanding it out, each coefficient is separately symmetric in all the BI, and symmetric in zeta through zeta to the fourth. So we can use the fundamental theorem of symmetric polynomials again to write down the polynomial here. What do we know about this? Well, the 4 quadruples of conjugates should end up clumping together, and so this should factor as 4 quartics. And if that's the case, the sum of each quadruple is the negative coefficient of x cubed. So we need to factor this degree 16 polynomial. How do we do that without a computer algebra system? Well, we know how to factor it mod large primes, again with Cantor-Zassenhaus. So let's try some large primes. They should be 3 or 7 mod 10, because those are the ones that don't split Q adjoin zeta 5. So we try 127, and we get these 4 polynomials. And we try 257, and we get these 4. Matching coefficients to suss out the negative ones, we end up with these factors. If you feel like it, you can expand out the product of these and check that you do get the polynomial we found earlier, but these are its 4 factors. And why do we do this? Because now we know that the 4 quadruple sums are -1, -1, -6, and 9. And these are expressions in the CI, since the BIs are, so plugging them in and expanding everything out, and factoring out each coefficient, we end with 4C4 minus C1 minus C2 minus C3. And so we collect the 4 expressions, 4 times 1 CI minus each of the others. To solve this, we add them to get C1 plus C2 plus C3 plus C4 equals 1. Then taking that and adding to each of the original equations gives 5C1 through C4 are 0, 0, -5, and 10, or C1 through C4 are 0, 0, -1, and 2. So then which is which? We can assume that C1 is equal to 2. Which one is -1? We'll figure that out by considering the sum of the BI's squared. On one hand, the sum is symmetric, so we can write it in terms of the elementary symmetric polynomials and get its value to be -21. But on the other hand, if we write B1 as 2 zeta minus zeta to the k and square it and expand, the cyclic sum of the first and third parts will each be -1, as will the middle term if k isn't equal to 4. That gives a sum of -1. But on the other hand, if k equals 4, the middle power of zeta equals 1, so the cyclic sum is actually 4. That does check out, and so b1 equals 2 zeta minus zeta to the fourth. Applying rho 3 times gives values for the other 3 b's. And so solving for zeta in this matrix equation, we get zeta equals 2b1 plus b3 over 3. So let's think about why that trick went right. The situation was we were trying to find some element in the field generated by some other element, and we gathered all conjugates of both and multiplied them one by one and factored the result. This is all completely general. Where we succeeded is we obtained an equation in the CI exactly because the conjugates of zeta were powers of zeta. So when we plugged in our values for the BI, the terms we got were still powers of zeta, which we were able to sum up easily. In general, what you need is knowledge about the sum of the conjugates of xi times xj if you're trying to write yi in terms of xi. Whenever you know that, you can apply the trick. Anyway, remember where we are. We know a value for zeta in terms of the BI, and we wrote the BI in terms of the roots Ri. So now we can enact step 5 of our outermost plan. Use the Kummer theory trick to compute the roots. If you didn't watch the previous video, sad. But it involves constructing an element with nice properties. Here we create this S, R1 plus R2 over zeta, and so on. What nice properties? Let sigma and tau be these elements that generate these two Galois groups. Sigma cycles the roots 1 to 2 to 3 to 4 to 5, and tau doubles each root index and subtracts 1, thereby fixing R1 and permuting the rest. Sigma has order 5, and tau has order 4, so every element is some power of sigma times some power of tau. And keep in mind that sigma fixes zeta, and tau fixes R1. How do each of them act on S here? Apply sigma to S and pull it through, sigma fixing zeta, and cycle the indices to get this here. This is almost S again, and if we multiply and divide by zeta, we can pull it out and actually get S. So sigma of S equals zeta S. We'll keep that for later. But now applying tau to S, pulling it through, cycling each index, and rewriting each denominator in terms of tau of zeta cubed, we end here, which again is almost S. If tau of zeta cubed equals zeta, then it is S, and tau of zeta cubed has to be some power of zeta, so does it equal zeta? I'm getting tired, so we'll finally remember that we're in complex number land. If we take the polynomial x to the fifth plus 10x cubed plus 20x minus 4 is equal to 0, and actually solve it, we get these 5 complex values. We let R1 be the real root, then we just randomly choose one of them to be R2, we choose the second one. And then complex conjugation always exists, and the only order 2 element that fixes R1 is to swap R2 and R5 and R3 and R4. So R5 must be the complex conjugate of R2. Then to decide which of the bottom 2 roots is R3 and which is R4, remember our equation for f, the projection of that polynomial. If R3 is the 4th root in this list, and R4 is the 5th, the computation for f gives negative 38.838. Close, but no cigar. So swapping them and computing the value of f, we actually compute f equals 40 up to machine precision. Thus, we line them up as such. And then we remember all the work we did. B1 is some well-defined combination of the r's. Computing it gives negative 0.809 plus 1.763i. And B3 was rho squared applied to that, which is some other well-defined combination of the roots, equaling the conjugate of B1. Notice that we don't know B2 or B4 since those were defined based on the Galois element rho, and we don't know the compatibility of rho with tau, which is exactly the problem. But either direction we go around the cycle, rho squared is the same element. And then zeta was 2b1 plus b3 over 3 as a complex number, this being negative 0.809 plus 0.588i. And we need to know tau of zeta cubed, so we start with tau of zeta, being this combination of tau of b1 and tau of b3. and we sidestep the values of those in terms of b2 and b4 and return to their definitions in terms of the r's, and evaluate it, and again, up to machine precision, we do get tau of zeta equals zeta squared. So tau of zeta cubed equals zeta squared cubed, which is zeta, like we wanted. We'll return to the significance of that in a moment, but first, let me tell you a story. It's called The Tragedy of x to the 5th plus 5x cubed plus 5x minus 1 equals 0. Suppose we wanted to solve this instead. We do the same prime factorization statistics, and get the same Galois group, and learn that the splitting field still contains zeta 5. We can run through the same computations of a through j to get integers for each in the same way. If we compute the same projection, it satisfies a degree 4 equation 2, and the same summation trick works to give the sums of 4, 4, -1, -6. Solving them in the same way, we find b1 equals zeta to the 4th plus zeta squared minus zeta, and inverting the matrix gives zeta equals negative b1 plus 2b2 plus b3 plus 3b4 all over 5. A little more complex of an equation, but nothing too bad yet. And then we compute the roots and the bi's, and the first one is negative 0.809 plus 1.314i. The other three, in some order, are these complex numbers. It turns out that it needs to be in this order because swapping b2 and b4 here doesn't give a root of unity. But in any case, we get zeta being this particular one, and applying tau can be done with the values of bi in terms of ri. We get this complex number, which is approximately zeta cubed. That's bad because s being fixed under tau is dependent on the fact that tau of zeta equals zeta squared. That is, there needs to be a compatibility for how tau moves roots around and how tau acts on zeta, and here there just isn't. And so if we actually compute the roots, we get these here. The fact that we needed the root 5 inside the 5th root has the same reason as the fact that the zeta incompatibility occurred. Remembering why we did this, we have this s, and we proved that tau of s equals s, and sigma of s equals zeta s, which when raised to the 5th power means that s to the 5th is fixed by both sigma and tau, which means it's in Q. This is why checking that tau of s equals s was important. S is the 5th root of something in Q, whereas in the tragedy, that s was the 5th root of something in Q adjoins square root of 5. Anyway, so s to the 5th is rational, and its 5th root s is still fixed by tau, so it can be written in terms of only r1, but it's not fixed by sigma, so it's not in Q itself unless it equals 0. That was the Kummer theory trick. Cook up this combination so that it gives useful results when tau and sigma are applied to it. And notice that it might be true that s equals 0, we had freedom of choice to which zeta we divided by. And they can't stop all of us, so we could have just changed out one zeta for another in what follows. Well, what is s? Unfortunately, we're not done with the heavy math just yet. Where we are right now is, we have this polynomial in terms of r1 through r5, and it is ostensibly fixed by tau. And so we don't need to do this here, but remembering that the projection is idempotent up to a factor of 4, we can apply tau 3 times to it and average them out to get the same value, but which is cyclically symmetric in R2, R3, R5, and R4. And then what do? We want to write each cyclically symmetric sum in terms of R1 because we should be able to. A good place to start is the values a through j we found way back. Fixing a power of r1 in any of the variables, the coefficient of that power should be cyclically symmetric. So we'll write a new set a1 through j1 and build up a new library of all cyclically symmetric polynomials in r2 through r5 in terms of r1 alone, in order to write s in terms of that library and thus in terms of r1. As an example, a was equal to r1 plus r2 plus r3 plus r4 plus r5 and equaled 0. So moving r1 to the other side, we got our first new variable a1. Similarly, b was the symmetric sum of degree 2, but the coefficient of r1 is r2 plus r3 plus r4 plus r5, and that equals a1, which is negative r1. So moving that to the other side, we get b1, which equals 10 plus r1 squared. And in the same way as we generated a through j, we can generate a list of cyclically symmetric polynomials a1 through j1 so that every other such is a polynomial in a1 through d1 plus f1 times a polynomial in a1 through d1 plus g1 times a polynomial in a1 through d1, etc. And behind the scenes, we can build the library in the same way as before, and writing out the coefficients in a through j, we can turn them into polynomials in a1 through j1. The first four can be easily solved for a1 through d1, and the fifth just becomes the original defining equation for r1, which is why there is no e1. But then the other five equations are linear in f1 through j1, so we have five linear equations in five variables, and doing the linear algebra off screen, we get these five values. Notice the denominators there. They're all the same, but they're ugly and get in our way. So the usual way to deal with this is to use the Euclidean algorithm on that denominator and the defining equation of R1. Notice here the second term of each product, to get a combination of them that equals a non-zero constant. If we take that and plug in x equals R1, the defining equation goes away because it's 0, and we're left with the product of two things equaling 36. So we maneuver it to get the denominator equaling an actual polynomial in R1. So we plug that in, reduce high powers of R1 down using R1 to the fifth equaling negative 10 R1 cubed minus 20 R1 plus 4, and we get this very nice set of values for the new variables. And remember, we want to rewrite S using this. We pull up the value that we found for zeta and multiply by R5, since that's the term that is multiplied by only zeta, or divided by zeta to the fourth. The final four terms in S's sum are just powers of tau applied to this, as we constructed, so this sum can be written in terms of A1 through J1 with our behind-the-scenes dictionary. We get this ugly mess, but we know what each of those are in terms of R1, so we plug them in, reduce again high powers of R1, add back in the first R1 term we ignored in S, and end with negative 20 thirds plus 5 thirds R1 minus 20 thirds R1 squared minus 5 sixths R1 to the fourth. This is S. This is the thing that gives a rational number raised to the fifth power. This is what we were looking for, and we were able to brute force it without any stupid Olympiad tricks. So we raise it to the fifth power, reduce again, and end with negative 12,500, which is negative 5 to the fifth times 4. So we can divide S by negative 5 and get the fifth root of 4. We're almost done. Now we take powers of this equation and reduce large powers of R1 again to keep everything only up to R1 to the fourth, and we get 5 equations which we can again form into a matrix. We invert the matrix, and look at the second row to finally conclude that R1 equals fifth root of 8 minus the fifth root of 4. Look at this. We earned this. The Olympiad student and the math professor have never done this amount of work for this problem, and we did. Sit and enjoy it for a minute. We solved a degree 5 equation with nothing but brute force, and ended with the same exact solution we knew at the beginning, but we didn't rely on any tricks, so we're much better prepared for any other question that could come our way. So let us review the path and techniques we used. First, remember the first thing we can do is use the Chebyshev density theorem, factor the polynomial mod lots of large primes to get cycle information about the Galois group. Second, keep in mind that the set of split primes is a sort of signature for the field. This isn't really useful except for the roots of unity fields because there's not any nice characterization for split primes of any field besides using modular forms, but roots of unity fields are exactly when we want to use it anyway. Third, notice how pretty much every question we asked about the Galois group or the splitting field came down to factoring an explicit polynomial, either with a rational root or into polynomials with conjugate roots we understand. In fact, we can always compute the full Galois group by repeatedly asking questions of the form, does this polynomial with coefficients given as polynomials in the coefficients of my polynomial have any rational roots? And when you know the answer is yes, it sometimes is kind of neat to calculate the polynomial and see that it actually factors, because you feel like you're cracking the problem open. Fourth, the Kummer theory trick is the thing that really helps us to go from a cyclic Galois group, which we know should be a root extension, to actually finding that root extension. It's indispensable if you know you can solve the given polynomial by radicals. And fifth, If you're doing questions like these, they will often involve a lot of computer algebra, and there's often a lot of different ways to go to the same place, but they're usually not any easier than each other. So don't shy away from it, buckle down, and find out where the limits of your crappy Python implementation of polynomials are.